Okay, so let's see if we can get a handle on where we are so far. Going back to my original example, I'm looking to solve this differential equation, and what we just concluded was that we need this to be true in order to find out what u1 and u2 are going to be. All right, so if we look at the homogeneous, the complementary equation, that's y double prime plus y is equal to 0, which will give us solutions of y1 equal to the cosine of x and y2 equal to the sine of x. So essentially what I'm interested in doing is taking that y1 and y2 and plugging them into this equation that I've got up here. So I have y1, I have y1 prime, I have y2 and y2 prime, and then f of x is going to be the tangent of x. So let's just kind of plug that stuff in and see where that leaves us. So I will be looking at u1 prime times y1, which I've said is the cosine of x, plus u2 prime, which I don't know what that is, times y2, which is the sine of x. And then the second equation is going to be u1 prime times y1 prime, which is the derivative of cosine. So that will be negative the sine of x, plus u2 prime times y2 prime, which is the derivative of sine. That is the cosine of x. I need this first equation to be equal to 0. I need the second equation to be equal to the tangent of x. So essentially what I have now is a system of equations. And that it's not a very normal system of equations. Probably at this point you've never seen a system of equations like this. We're looking for not for constants as solutions, but actually for functions as solutions. I need to find some function u1 prime and u2 prime that are going to make both of these things end up being true. Now, what I'm going to end up using to do this is called Cramer's rule, which is a way to solve systems of equations. And in general, it's not a very good way to solve systems of equations. It's not very good except when it is very good. And this is an example where it is very good. So really quickly, let me show you an example of Cramer's rule just so that we can get a feel for it before I start looking at this particular equation. Let's say, this is back in Algebra 2, that you had a system of equations that was x plus 2y is equal to 3 and 3x plus 4y is equal to 5, right? And so most of us would probably do this by substitution or by elimination. Cramer's rule asks you to do the following. It asks you to take the determinant of what is called the coefficient matrix. That is all of the coefficients of the x's and y's. So I ignore this last column. And that's a 2 by 2. I take the product of the main diagonal and the product of the off diagonal. So that would be 1 times 4 minus 2 times 3. So that would be equal to negative 2. Then we calculate what is called d sub x. That is that I go back to the same matrix, but I keep the second column, that column with the y's, I keep that, but I replace the x column with these numbers that were over on the right side. So 3 and 5. Then I take the determinant, multiply that way and that way. So 3 times 4 minus 2 times 5. So that's going to be 12 minus 10 is 2. And then I calculate d sub y in a similar way. I replace the y column with the 3 and the 5, and I leave the x column the way that it was back up here in the original one. Multiply in this direction, so 1 times 5 minus 3 times 3, that's 5 minus 9 is negative 4. So I find d, which is the determinant of the coefficient matrix, and then these two determinants here. And it turns out that x will be equal to d sub x divided by d, and y will be equal to d sub y divided by d. In this case, d sub x was equal to 2, and d was equal to negative 2, and d sub y was equal to negative 4, and d was negative 2. So I would get that x is equal to negative 1, and y is equal to 2. Cramer's rule in solving a question like this is really not very efficient. If you did this by the elimination method, you would get this done much, much quicker than we're getting it done by doing Cramer's rule. But Cramer's rule is going to be really a nice way of going about solving this system of equations here. Okay, so Cramer's rule. Keep in mind that our variables are u1 prime and u2 prime. So they're taking the place of x and y in our previous example. So d are the coefficients. What is it that is being multiplied by u1 prime and u2 prime? D is the cosine of x, sine of x, and negative sine of x, cosine of x. And I'm going to take the determinant of that. Now at this moment, you should be kind of thinking that that looks familiar. In fact, it looks so familiar that I am not going to call this D, I am going to call this W, because it is in fact the Wronskian of the complementary solutions. So this is the Wronskian of y1 and y2. Now for us, what does this turn out to be? Cosine squared of x minus a negative sine squared, so that's going to be plus sine squared of x, so the Wronskian ends up being 1. So that's that value of D from before. So then I will find W sub u1 prime, where I am going to replace the u1 column with 0 times the tangent of x and leave the u2 column the way that it is. That would be 0 in this direction, and then sine tangent times the sine in that direction. We're going negative, so that would be negative sine of x times the tangent of x. And since I know where this conversation is going, tangent is sine over cosine, so this is negative sine squared of x divided by cosine of x. And then we move to the u2 column, which is w sub u2 prime. So I leave the first column the same, so that's cosine negative sine. And I replace the second column with 0 times the tangent of x. I will get cosine times tangent and 0 in this direction. So cosine of x times the tangent of x. Tangent is sine over cosine, so this is the sine of x. All right, so what did I get? I got that the Wronskian, the determinant of the coefficient matrix, is 1. I got that the Wronskian for u sub 1 prime is equal to negative sine squared over cosine squared, and the Wronskian for u sub 2 prime is equal to the sine of x. So that means that, again using Cramer's rule, that u1 prime is going to be equal to the Wronskian with the u1 prime substituted. That was negative sine squared of x over cosine of x, all divided by 1. And that u2 prime was equal to the sine of x, all divided by 1. Now I want you to just double checking here to make sure that I did that. All right, so I want you to remember that what we were looking for was u1 and u2, so that the particular solution was equal to u1 times y1 plus u2 times y2. I now know what u1 and u2 prime are, so you can see the calculus coming. I need to integrate in order to find out what u1 and u2 are going to be. All right, so u1 is going to be equal to the integral of negative sine squared of x divided by the cosine of x dx. Hopefully you remember your second semester calculus. The easiest way to do this, I'll put the negative out in front, is to replace the sine squared with 1 minus cosine squared of x divided by the cosine of x dx. Then this would be, again, leave the negative out there, that will be the secant of x minus the cosine of x dx, and then those are both things that we can integrate. The integral of the secant, I am looking at our integral card and get that the integral of the secant is the natural log of the absolute value of the secant of x plus the tangent of x. And then the integral of negative cosine would end up being negative the sine of x. There is a plus c here. We are not going to need it for the same reason that we haven't needed things before. For right now, just take my word for it, and then I'll justify that when you see how we put the solutions together. So there's u1. u2 prime is the sine of x, which means that u2 will end up being the integral of the sine of x dx, which is negative the cosine of x. And again, there's a plus c that we are not going to need because of the way that we're going to put these solutions together. So that means that our solution to this differential equation is going to be the complementary solution that we found all the way back at the beginning. c1 times the cosine of x plus c2 times the sine of x plus the particular solution. The particular solution is u1, which is this right here. I will put this negative in and I'll rearrange the side there, the direction. So it's the cosine of x times u1, which is the sine of x minus the natural log of the absolute value of the secant of x plus the tangent of x plus the sine of x times, this is y2 times u2, which is minus cosine of x. So this is our solution to the differential equation, and I just want to remind you that the differential equation was y double prime plus y is equal to tangent. What a cute little innocent looking differential equation that all of a sudden exploded into this big of a solution. The last thing that we should do with this problem is, check and see actually if it worked, because there's no way that we could go through this entire conversation and that you guys could say, oh yeah, sure, that totally looks like the answer. So I'm using Mathematica to check my answer. I want you to verify that I have what we just came up with, that my solution will be y is equal to c1 times the cosine plus c2 times the sine, and then the particular solution comes in. Cosine, which was y2, which was y1 times what we found to be u1. It turns out with Mathematica, I don't need to put that ABS, the absolute value in. It does a better job without that. Plus y2 times u2. Now, you may recognize here immediately that like this term and this term are going to cancel. That's algebra. I'm actually going to leave it in just because I want to make sure that this does in fact work out. So I'm going to execute this command, which tells me, which sets up, okay, there is my value of y. I don't need the first derivative. I only need the second derivative. So this command is going to find the second derivative. So it's taking the second derivative of all of that stuff up there. Let's just pause and admire that for a second. Yep. Then I'm going to take the second derivative and add it to the first derivative. And it ends up looking like that, which is just absolutely fantastic. This is supposed to simplify to the tangent of x. That is not obvious to me at all that does simplify to that. But then if I execute the simplify command, bang, there it is, the tangent of x. So it turns out that this is, in fact, the solution to y double prime plus y is equal to the tangent of x.